this presentation is going to go through a couple different regression outputs just so that you can become a little bit more familiar with the different things that I look at and kind of a process that you can go through every time you look at a regression output. But before we go into that, let's go back to the idea of correlation analysis. So here we're looking at the continuous variables in a German credit data set that's publicly available on the SAS website. And so let's say we're wanting to use credit data to predict the amount of loans taken out. One of the first assumptions that we look at with linear regression is that they are linearly related. And so the way you evaluate if they are linearly related is through a correlation analysis. So the closer the values are to 1 or -1, the more linear that relationship is. And so let's say we have the hypothesis that age and amount are, the age of my account is really useful to predict my amount of my loan. But here we see that we have a correlation value of 0.032716. Like I said, that's probably much closer to 0 than 1, so it's probably not going to explain very well, but let's look at the output that we get when we run the linear regression for it anyways. The first thing that I'm going to do is check the global test, also known as our omnibus test, which investigates if the independent variables have coefficient values whose differences from 0 is statistically significant. Typically, you're going to use the 0.05 level. And so it looks like the F test. That's really what you're doing here. And so your F statistic is calculated by taking your mean squared of your model divided by your mean square of error. And so here we see that our global test is not statistically significant, which indicates that none of my predictor variables, which in this case is just age, has a slope that is statistically different from 0 at the 95% confidence level. So in this case, I would not determine that age alone would be enough to make a statistically significant model. But for the purposes of discussion, let's continue going through this output to discuss a few other key ideas. So the next thing that we do is we look at the R squared to assess our fit. Since this is a simple linear regression, we don't need to even look at the adjusted R squared. The only thing we worry about is R squared on this. And R squared shows the proportion of the variance in Y that's explained by the variance in the X variable. And so here we have this correlation value. And so once again, remember, if we're just doing a simple linear regression, we don't have anything else to influence these relationships, our correlation value squared is going to be the same value as my R squared value. The other thing that we have in these tables is we have our parameters. So these parameter estimates are those coefficients that you see when you write your linear equation, and then your standard error value, and then you get your t-value. So what your t-test is looking at is the difference between your parameter estimate or your slope value and 0 divided by your standard error. And so when you look at your t-test and find the associated p-value with it, you see that the p-value for age is going to be the same as our p-value for our f-test, because in this case, remember that f-tests are a whole bunch of t-tests done at the same time, but if we only have one group, which would be age, then that significance should be the same. So now let's look at duration to predict our amount. So once again, the first thing that I'm going to see here is that my global test is statistically significant at the 0.05 level. Once again, since this is a simple linear regression, the results of my f-test and my t-test are going to be the same in terms of whether or not this is statistically significant. Because remember here, we're saying, does one of my slopes have a difference from 0? And here I only have one slope, so it really should be different from 0. Once again, since this is a simple linear regression, if I go back to that previous slide and I look at my correlation value and I squared, I get my R squared value. But once again, my adjusted R squared value is not very informative because remember, adjusted R squared is used to penalize this model fit value for complexity. But when you only have one predictor variable, you don't have that complexity issue to even consider. you would write your final equation for your model as being amount equals 146.29680 times duration plus 213 plus 21603. Now let's look at a model that has a whole bunch of predictor variables. So I've taken the same data set and now I've thrown all of our continuous predictor variables into the model. The first thing that I see is that the global test is statistically significant. Since this is a multiple linear regression, we see that our p-values are going to be all over the place for our t-test, because now we're looking at the combination of all of these t-tests being conducted at the same time. Now, when we look at those t-tests, we see that not all of the predictor variables are statistically significant at the 0.05 level. So sometimes you need to keep them when they're not statistically significant. But the thing that you need to keep in mind is the more predictor variables you have, the more complexity you have in your model, which is going to inflate your R-squared value and can cause problems with interpretability and other issues. More importantly, overfitting your data so that you're modeling the noise and not necessarily what you're trying to model. So one of the things that we also want to look at, since we have a whole lot of predictors, is looking at multicollinearity. One of the fundamental assumptions of multiple linear regression is that all of your predictor variables are independent of one another. And so they need to be what we call non-collinear. And so we're looking here for our variance inflation values to be below 3. Because as they get bigger, they become a bigger problem. And so when we assess this assumption, we can see that we have we're looking at how much of our variance is explained by one variable overlapping with the variance that's explained by other variables or a combination of variables, which will inflate your R-squared value. And sometimes when I say inflate, sometimes it makes it bigger, and actually sometimes it can diminish it as well. With model fit, one thing that we want to notice is that we have 5 variables whose slopes are not statistically significant. And so, like I said before, we have additional complexity inflating our R-squared value here. Sometimes you want to keep them for the purposes of your research, but it really comes down to what your domain knowledge is of the problem and the research area in general. And so here we've taken the same model, but we've removed those non-significant predictor variables. And here we see that my R-squared value is actually a little bit lower, which we expected that because we don't have as many predictor variables. But my adjusted R-squared value actually went up. And so I would, depending on the scenario, I could see an argument for using the second model. But if you had some reason to keep some of these previous values into your model, as long as you explain it, you're fine. So you really have to have some judgment there. Now let's look at a different set of data where we're looking at continuous variables to predict the selling price of homes in a neighborhood that is in a suburb of LA. So here we see that the number of bedrooms and bathrooms have extremely high variance inflation factors. We have 35 and 42 for these variance inflation factors. And that would make sense because houses that have more bedrooms also tend to have more bathrooms. We also see that size has a larger, albeit not as large, width value of a 5. So the first thing that we're going to do is essentially stepwise backwards regression, where you go back and you start removing variables one at a time to see how it affects your model. So looking at this, since bedrooms and bathrooms both have very high variance inflation factors, let's go ahead and take bedrooms out of the model because their variance inflation factor is much higher, which means that it's overlapping not only with bathrooms, but probably overlapping with size. And so here's that resulting model. And we see that this resulting model is still statistically significant, and we still have a huge R-squared value. The removal of bedrooms from the model only decreased the R-squared and adjusted R-squared just minimally. And so we see that the variance inflation factor for the bathrooms has gone down quite a bit, after we removed our bedrooms. But we still see that size and bath are still giving me some unacceptable variance inflation factors. So once again, that's also going to make sense because if I have a larger house, I'm going to have more bathrooms. So here, since, if I'm looking at which one to take out, if I want to take out bathrooms or if I want to take out size, I would look at taking out the bathrooms first because size is our only predictor variable that has a statistically significant slope. So after I've removed bedrooms and bathrooms for a model, we're left with a model that still has a statistically significant omnibus test and 90% of the variance explained, and we're no longer violating the assumption of non-collinearity. So those are all things that we want: high explanation, high predictive power. We want it to actually be modeling something that is actually different from zero. And we do want to make sure that all of our predictor variables are kind of staying in their lane. And so here, if we just looked at, since we only had one predictor variable that was statistically significant in this model of just size, let's just go back to our simple linear regression with this set and look at the resulting model with that. And here we see that evaluating the t-test for the slope, we see that that's the only one that's significant, and its r-squared is 90.5% anyways. And so since it's not much different from the model, you might want to argue that the simpler model is a easier one to generalize and explain. So hopefully going through these different outputs kind of helps you think about the processes of how do you interpret a model, what order do you need to look at things in. But if you need further explanation as to where the calculations for these variables come up, or for these values come up, please refer to any of the regression presentations that I also have included in the course.